So in video 3 we're going to look at solving exponential equations. So to start with, we'll start with a very simple example. Here we have the equation e to the x equals 0.343. So I'm going to go ahead and rewrite that equation. E to the x equals 0.343. And what we want to remember is that the logarithm base b of x was constructed to be the inverse function for exponentiation base b to the x. And what that means is that if we take the log base b of x and we input an exponential function b to the x into log base b of x, the x will pop out. The log base b will cancel the exponentiation base b because they're inverse functions. In the same way, for example, we know that for x greater than or equal to 0, we know that the square root of x is the inverse function for x squared. So when we pop x squared into the square root function, the square root cancels the squaring and gives us the x out of the equation. So what we can do here is identify what the base is. The base is e, so we could use the inverse of exponentiation base e, and we could say, hey, I'm going to take and apply log base e to both sides, but we know that log base e is represented with the natural log function. So we're going to take the natural log function, which is log base e, and we're going to make both sides of our equation inputs into the natural log function. So we'll input e to the x into the natural log function. We'll input 0.343 into the natural log function. And the log base e will cancel exponentiation base e and give us the x out. The input variable pops out and we get x equals the natural log of 0.343. And this is the exact answer. So if you're in a homework problem where they ask for an exact answer, this is it. If you're asked to approximate, you would put your approximation symbol in. You would go to your calculator. And we would put in the natural log. Here's our natural log key. The natural log of 0.343, and we'd hit enter, and that's going to generate a result, negative 1.07. So we go back from the calculator, negative 1.07 is an approximation of the answer. So a little bit more complicated example. In this case, we still want to use the inverse function for exponentiation base e. Here's our exponential function with base e. So we know that the natural log function is going to be the inverse function, but the first thing that we need to do is isolate the base e exponential function. And we're going to isolate it by using algebra. So we'll go 250 0.05 x plus 1 in the exponent position plus a 175 is equal to 1175. Rewrite the equation. We need to isolate the base e, so I'm going to go ahead and subtract the 175 from both sides first. So we'll get 1,000 sitting over here, and we'll be left with the 250 e to the 0.05 x plus 1. I still don't have the base e exponential function isolated, so I'm going to divide both sides by the 250 to get that coefficient off of the base e. 250 divided by 250 is 1. That's going to leave us with e to the 0.05 x plus 1 on the left side, and we're going to get a 4 on the right hand side. And then we want to recognize that we need to input this base e. We've got the base e isolated now on the exponential function. We're going to need to input it into the natural log function, and we'll have to do the same thing to both sides. Now when you do this, so common student error that gets marked down significantly in exams, you can't just throw an ln here and an ln here and say that you've taken the natural log of both sides. You can't write the natural log here and here. The natural logarithm is a function. This is a function, and we put things into the function. So the e to the exponent needs to go into the natural log function. The 4 needs to go into the natural log function. And I know textbooks are sloppy and they write it like this frequently. I don't like this notation because I think it de-emphasizes the fact that you're working with a function, and so I want to see people using function notation. So the key here is the natural log is going to cancel the base e exponentiation. That's going to just leave us with the exponent. The exponent pops out for us. And now we can isolate x by subtracting 1 from both sides. And then we can divide both sides by 0.05. Divide both sides by 0.05. That's going to give us a 1x. X, and then if I want to approximate this, this is the exact answer. So I could just write ln of 4 minus 1 over 0.05. If I were being asked for the exact answer, this is it. This is exact. If I'm asked to approximate it, I'm going to go x is approximately equal to, and you would use your calculator to do the approximation. And we need to be careful when we're doing this that we keep the numerator right here in parentheses when we put this into the calculator. If we don't lock the numerator into parentheses, we're going to get an incorrect evaluation by the calculator. So I'm going to throw this off to the side, clear the calculator screen. I'm going to put the numerator into parentheses. So parentheses, natural log of 4, close parentheses, minus 1, close the numerator parentheses, and then divide by 0.05, hit enter. About 7.2, probably good enough for us. So x is approximately 7.2. All right. So next example. This one's different than the others in the sense that the exponentiation isn't with a base that the graphing calculator can handle to give you an approximation. Your graphing calculators, if you're using one, have log base 10 and log base e available to you. So one way that we could work through this, and it would be nice if we could do it this way, and perhaps if we're using, for example, GeoGebra, we can do it this way. But this is exponentiation base 9. So the inverse function would actually be log base 9 of x. So the most natural way to attack this would be to go log base 9 of everything on the left-hand side and go log base 9 of everything on the right-hand side. And so the only issue with doing, if we did this, it'd be nice because log base 9 would cancel the exponentiation base 9, and it would just cleanly leave us with 5x minus 3. But the calculator isn't going to be able to handle this. So what you would need to do then is to do an approximation in a calculator, you would need to do the change of base formula. You would need to remember that the change of base would allow you to use, for example, log base 10 of 78,462 divided by log base 10 of the base 9. We would need to convert it either to log base 10 or log base e, because that's what our graphing calculators can handle. But we don't need to work log base 9 and then do a change of base if we don't want to. So what we could do, that would be one way to do it. But the other thing that we could do, and what you'll see is we get the same result, is just start with log base 10 or log base e. You choose which one you want to use. It doesn't matter. Your calculator has both of these options. Pick one. This time I'll do log base 10. So I'm going to make the left-hand side the input into the log base 10 function. And then when I do that, I can use the log properties. I can use the power property to note that, hey, I have an exponent on a base 9 inside a log function, and my exponent properties allow me to bring that exponent down in front of the logarithm as a product. So I can bring the 5x minus 3 down and multiply it by log of the base, which in this case is 9. And I would still have a log base 10 of 78, 462 on the right hand side. And then right away, before I distribute into the parentheses or do anything like that, I'm attached via a product. So the simplest thing to do here is just right away divide by the log of 9. And I'd have to do that on both sides. Here's the log of 9. And if I do that, what you notice is that when I had the log base 9 here, this is how you applied the change of base to it. You got this via change of base. So the change of base flows naturally out of just using the power rule for logarithms and then dividing out by the log of the base that you're left with. So this divided by this is 1. That's going to leave us with the 5x minus the 3. And I still have the log of 78, 462 over log of 9. And I'm going to add, now I need to isolate that x. I'm going to add 3 to both sides. That's going to give me log 78, 462 divided by log of 9. I added 3 to both sides, which leaves me with 5x. And to get 1x, I'm going to multiply the left-hand side by a fifth. So I'm going to go ahead and multiply the other side also by 1/5 in a parenthesis so that that 1/5 distributes into everything on the right-hand side. A fifth of 5 is 1, so I get 1x equals a fifth of the log of 78, 462 over log 9 plus 3. And this is the exact answer. If I need to approximate it, then I'm going to go to my calculator. I'm going to say, hey, x is approximately equal to. I'm going to keep that, and then I'm going to input this mess into my calculator. So I'm going to have 1/5, so 1 divided by 5 of parentheses. I used log base 10, so I'm going to use my log button. 78, 462, 78, 462. Close that logarithm parentheses off. And then it's divided by the log of 9 right here, divided by log 9. And then I need to add my 3 on to that fraction, so plus a 3, and then close the entire parentheses and hit enter. And I've got about 1.6-ish. 1.6, 1.63, depending on how you were asked around. 1.63. We'll go to the hundredth this time. So here's an example where we have a mismatch in bases. So I couldn't go log base 2 to both sides and have it cancel both sides. I can't do log base 3 of both sides and have it cancel. So I'm going to need to choose either the log function or the natural log function, which are the keys that show up on my calculator. I'm going to go ahead and use the natural log function this time. So I'm going to take both sides and input them into the natural log function. Except you have to input it correctly into the natural log function. And then I'm going to use that power property of logarithms to say, hey, I have a base to an exponent inside a logarithm, so the exponent can come down in front. I have a base to an exponent, I'll be able to bring the exponent down in front. So on the right hand side it's going to be x natural log of 3, and on the left hand side it's going to be x plus 1 times the natural log of 2. I can either divide both sides by the natural log right now, or I can choose to distribute the natural log into the parentheses. Either way, at some point I'm going to need to get everything with an x on one side and everything without an x on the other, because I'm trying to solve for x. I think this time I'm going to go ahead and distribute. I think it's probably more efficient not to, but I'm going to do it this way anyways, because some other log properties are going to pop out if I do it like this. So x natural log of 3, I'm going to get x times the natural log of 2 plus natural log of 2 times 1 is natural log of 2. And then to get the x's all on the same side, I'm going to subtract x natural log of 2 from both sides. So on the right hand side, I'm going to get my x natural log of 3 minus my x natural log of 2, and I'm left with just a natural log of 2 on the left hand side. And then what I'm going to do is factor the x out, which will leave me with natural log of 3 minus natural log of 2 equaling the natural log of 2 on the left hand side. And now I can apply a log property here. Hey, I have the difference between two logarithms with the same base, which means I can write those as a quotient. Natural log of 3 divided by 2 equals natural log of 2. And then I can divide both sides by the natural log of 3 halves. Natural log of 3 halves. Natural log of 3 halves divided by natural log of 3 halves is 1. So sliding up the page here, I get x times 1 is just x. And x is equaling on the left hand side, we have natural log of 2 divided by natural log of 3 halves. This is the exact answer. If I want to approximate it, again we go to the calculator. And we pop this into the calculator. So I use the natural log this time, so I'm going to go ln of 2 divided by ln of 3 halves, so 3 divided by 2, and then hit enter, and about 1.7-ish. So let's bring this back to full screen, about 1.7. All right, final example. So these are the ones everybody always enjoys the most. These are the ones that have the variable that you're solving for down in the denominator position. So you've got to dig everything out of the denominator. So I'm going to rewrite my equation. This is 80 over 1 plus 15e to the negative 0.06x. And this equals 50. So my first step is going to be to multiply by the denominator on both sides so that the denominators cancel. So that's going to give me a 50 times 1 plus 15e to the negative 0.06x on the right side, and just a measly little 80 on the left. And now instead of distributing the 50 into the parentheses, which would be a legitimate move to make, and things would work out fine if you did it that way, it's going to be more efficient while this is connected as a product to divide both sides by 50. It's going to simplify things tremendously to do it that way. So 80 divided by 50 reduces to 8/5. So here's my 8/5, and that's going to leave me with 50 divided by 50 is 1. So 1 times the stuff is going to leave me with the stuff. And then I'm trying to get this base e by itself, so I can use the inverse function natural log of x to cancel that base out. So I've got to isolate the base e, so I'm going to subtract 1 from both sides, but I need a common denominator of a 5, so my form of 1 that I'm going to subtract is 5/5 minus 5/5, so that's going to leave me with a 3/5 equal to 15e to the negative 0.06x, and then I can divide both sides by 15. I could divide both sides by 15, but it's going to give me a complex fraction on the left-hand side. So I'm going to restrain myself from doing that. And I'm going to recognize that dividing by 15, I'll get the same result if I just multiply 15 times its reciprocal 1/15. 1/15 of 15 is 1 e to the negative 0.06x. And I can simplify this fraction a little bit. 1 times 1 is 1. 5 times 5 is 25. I'm going to walk this up here. I'm going to use the natural log function now. I'm going to input both sides of the equation into the natural log function. And the natural log is the reciprocal of exponentiation base e, so those are going to cancel each other and leave me with just the exponent. And then I'll divide both sides by, that's a horrible x. I'm going to divide both sides by negative 0.06, divide both sides by negative 0.06. Negative 0.06 divided by negative 0.06 is 1. That's going to leave me with 1x equals this mess over here. And this is the exact answer right here. This is exact. And if I'm being asked to approximate it, this is where I would probably move to my calculator and let my calculator finish that out. So what do we have? We have the natural log of 1 divided by 25, close the natural log function, and divide it by negative 0.06. I should get a positive number out of there, 53.65-ish. So 53.65-ish, 53.65-ish. And there you have it.